Hello and welcome to my channel Tech and Tech. In this video, I am going to try some hands-on experiment for absolute beginners in machine learning. So without further delay, let's get started. So I'm going to do the experiment in Python language. So first of all, we need to import some Python libraries. Okay, so the first Python library is NumPy, which we will be using for mathematical purposes. Okay, so it's the math library, and the pandas is mostly used for uh, data analysis and means data extraction. Okay, pandas is just for data set, read and write, and also it has some data analysis tools. And matplotlib is for data visualization. Okay, so these three are important libraries that we will be using in this experiment. So first of all, let's create our own data set from scratch. Okay, so we'll take two variables x and y. So we'll create them using numpy. Okay, so I will create an array of say 100 and let's display them. So I've created the value of x as from 0 from 99. So there are 100 elements in this variable x, and I will also create another variable called y. Sorry, y will be um, multiple of x. So let's take another variable m. So I will take m as 1.5, and we'll also take another variable called c, and we'll take it as uh, 2.3. So we'll use the typical expression y is equal to mx plus c. So it's a popular formula for straight lines. Okay, so y is equal to mx plus c is describes a straight line. That's all to it. So we'll receive y. Let's print it out. So this is our y. So if I plot x and y right now, I will use like plt dot plot x comma y, and I'll need another command to make the plot visible in a notebook. It's called um, plot the inline. Now if I run it, you can see it's a straight line. So it's working. So I will now add some noise uh, to that variable y. So it will be like y equals y plus some noise. So what would be the value of noise? Obviously np dot random, and um, let's see, there are so many random generators, so we'll use something. Let's see what we can use. um, there's so many choices. So let's try uniform. Okay, it's the easiest thing to do. So np 100 uniform, there will be 100 elements, so I have mentioned them like 100, and they will range from -1 to +1, I think. So let's try it and plot it again. Okay, let's see what happens. So nothing much, does not change anything, right? Let's see what is the output from uniform. Okay, single value. So I think that's the problem. uh, it should be one, sorry, it should be one, and there has to be something called size, right? Let's try. Yeah, so there is something called size, but it's not working as expected. uh, let's see. Okay, so let's try rand. It would be better, I guess. Yeah, there is some noise, but it's not so visible. Let's increase the value, like let's make it 5 times, I guess. Yeah, now there are some visible noise in the graph, so I'll do something. uh, okay, let's take this example. Okay, so we have some data here, x and y. In a typical machine learning situation, say we have to predict the value of y based on x. So it's kind of random, but it won't be 100% accurate, but still it has to be close enough to be used in real life applications. So let's try it. Let's try to predict the value of uh, y as close as possible. Okay, so to do that, the easiest way is to model another solution, say a function which will say predict, and it will take a value of called x, and it will return a value y. It will return y simply, calculated y. Now what is the value of calculated y? We have to find out using um, a variable um, x multiplied with some variable m plus c. Okay, so we don't know the value of m and c yet, so we have to figure out the value of m and c. So how do we do that? Well, we have to figure it out by ourselves, so that's the main thing. Okay, so let's try it out as it is, because we have already defined m and c somewhere above m and c, so it should work. But still, let's do it again. Random.rnd, and so that's m, same goes for c, and we're done. So let's try our function. Let's predict the value of x at x equals 0. So this is basically the value of c. Okay, because if we just print c, it's the same thing, because at x equals 0, x multiplied with m is also 0, so only c is the remaining. So let's try something like this, so it happens like that. So how do we plot the whole thing? So let's uh, print calculate y equals read, and we'll predict the value for all x. We'll pass in the whole array of x and we'll receive the whole thing. Okay, so actually basically the x is a whole lot of arrays, so it, it should have returned array, right? Multiplied by m, as x is an array, so if we multiply array with a number, so it will return an array. Similarly, if we multiply with m, it will return an array, and if we add it with any constant, it will return an array. But if we call in print, yeah, it is returning an array. So that's fair. So now let's do one thing. Let's plot the whole graph. Okay. So if I plot it, that's the graph of x and calculated y. Okay. So how do you know if it is the same thing or not? So let's plot both of them side by side. Not side by side actually. You know, overlapping. They will be overlapping each other. Let's see if they truly overlap or not. Okay. Yeah, they are not close enough. As you can see, the blue one is the predicted one and red one is the actual one. So right now, the as the function is not ready yet, we cannot predict the whole thing. So how do we make it right? So to make it right, we can just tune the value of m. Say for example, if we change the value of m from m to 0 and we run this whole thing again. So as you can see, it has changed the graph, the prediction values. So we have to figure out the value of m, right? So how do we do that? Let's do it practically. First of all, we have to find something called the error, the difference between the calculated y and the predicted y. So we already can get the calculated y like that and have error by subtracting um, y and calculated y, and we are expecting error to be a scalar number, not an array. Okay, error will have only a single value. So how do we do that? To do that, we will just use another function called sum. And by the way, as it can result in a negative value, we don't want that. We will just make sure that it is always positive, because uh, the error should always be positive, not negative. I'll explain it later, but for now let's continue with that. So let's see the value of error. So it is showing a huge value. By the way, this error is called um, absolute mean value. Actually it's not yet mean. Okay, so to make it mean, we just have to divide it by 100 and it's the absolute mean value. Yeah, so the error is 73. So we have the error. Now our goal is to reduce the error. The less the error, the better. So to do that, we can do one trick, like if we change the value, like let's say we have the calculated y. We'll change the we'll first create another function called uh, error. Okay, let's take it simple, error, and I'll pass it x and inside it will return the error. Okay, so we'll try another thing called, we'll just find the error first, e1, and then we'll change the value of m. So first of all we'll save the old value, old m. Okay, old m equals m, and then we'll change the value of m to certain value like m plus 0.1. Okay, we'll change a very little portion of m, and then uh, we will just um, find the new error, e2 equals c error or error x. Okay, so the change in, we have changed m by adding it, so we'll find the uh, change in error. So let's name it de. Change in error equals e2 minus e1. Okay, so actually we want the e2 to be less than e1, so e2 is less than e1, that means e1 minus e2 would be positive value, would give us positive value if it is decreasing. Okay, so let's take it like that. Okay, so we will add old m with something called the new, sorry, de. Well, change in error, we'll just add the change in error with the old m. So what we're doing is we're saving the old m value and then making a little shift in m. Now if the de value is positive, I think I should add like that, de is greater than 0, which means de is positive, which means it is decreasing. So I'll just add the new value of m should be like that, or it should be opposite, right? I think if it is less than, I mean it is, if it is negative, okay, if it is negative then we will take the old value, otherwise it's fine, it's fine. Okay, like we have increased the value of m and okay, we don't have to revert it. But if it's the opposite, if the error increases, then we have to uh, fetch the value from the old m, like the old m is better than the new m, so we have to get the old m, and instead of adding we'll just subtract it. Okay, the other way around, we'll just subtract it, and again we will analyze the new error. So we'll again check the e2, and if de is again less than 0, which means we don't have to change anything, old m is better than anything. So that's how we will train the model. So this is the we can say optimizer optimization algorithm I am going to use. Okay, so let's try it step by step. Let's make it a function. Let's first run it and see if there is any error. Yeah, there is an error. Okay, I have not run it yet. Okay, no error now. So let's call it train and select all of them. Mm, and I will train it and see the result. Oh, there is some error. Train is not defined. Okay, run it. Insertion. Oh, I have to, as it is inside a function now, I have to use a keyword, Python keyword called global. Global m. Okay, for now I'm just training the variable m. Let's see how it goes. Okay, let's try again. Is there any improvement? Yeah, it is aligning. As you can see, it is aligning to the red one, right? It is aligning. It is doing it best. So just by modifying the value of m, it has gone this way. It has reduced the error. Let's do one thing. Let's also print the error. Uh, error of x. Okay. So the error is 8 point something. Okay. So let's do one thing. Let's try this one again, and I'm going to train it. Okay. So initially the error is 63, then 58, 53, 48, 43. And the error is reducing step by step. Okay, gradually. So it settled at 8.95. Okay, let's try another thing. Let's do the same optimization algorithm for c, for variable c. Okay, so instead of old m, it will be old c. C. um, Everything is same, just m will become c, and the optimization to c will be done similarly. Okay, so I think I can add with a comma inside of global. I think it will work. Let's see whether it works or not. Let's see if the value of c, as you can see, the error is reducing a bit by bit, very slowly it is reducing. Okay, it is changing very slowly, and it has stopped changing for some reason. I think it is due to the value, which is zero point 0.1. Instead, if I just choose something like 0.1, then it would have worked, I guess. Let's try it. As it is experimental, so I think it's better to try something new. Let's see whether it changes or not. No, it remains the same. Okay, so it has reached a minimum error of 8.4. Okay, so let's do one thing. Let's try it again, because now we have both the m and c. Now let's try it from the beginning again. So both m and c are adjusting side by side. So now they are going to reduce the error 7, 6. So error has reduced to 6. Let's do one thing. Let's create a for loop and make it like 50. This way it will be a lot faster. Now it is not training anymore. Okay, so this is a very basic form of uh, algorithm. Like practically, this thing is not used. More advanced things are used, but for starters, we can use this one. Very basic, simple concept. The drawback is the value is kind of rigid, so that's the only drawback. I mean, if you are doing derivative, if you are applying derivative in that, the value won't be 0.1. It's in case of derivative, the value is kind of like very small, like 0.000000001, something like that. We calculate when we calculate derivative, uh, it's more accurate than this model. So the thing is that even though it's not very accurate, but we can get close enough like that. Actually, I found one error. The error is over here because we have calculated we have calculated E2, but we have not calculated DE yet. So we have to write the statement first. Okay, so we have missed this portion only. So as for variable C, it's a copy, so we have to fix in both places. So it's done now. We have DE calculated right here, and it will decide whether it will keep the old value or it will stay the new value. So that's how it works, right? Let's see. Let's see if there is any change now. Let's try this one. Now the error has reduced considerably from 6 to 4. Okay, so let's do one thing. Let's also add uh, e. Okay, so let's give it a name called e, and we'll control the value of e from there, and we'll name it like e, just a constant. Okay, so that we can tune them more and less. So the thing is now it's working fine. Why? Because a little change in E, I mean a point that it became very sensitive. So a little change in AM will occur more error. So it's better to take a little step. Like the changes that is required right now is very less than 0.01. So we have to decrease that and try again, and you can see the value reduces. Okay, let's try again and see. Yeah, let's go for 500 times and see the value reduces. So in other word, it became sensitive. That's all. Let's try it for 5,000 and see. Just more sensitive. So you can see the error reduced considerably. So that's how it works. So if I make it more sensitive, maybe just maybe it will reduce even more. Let's see. No. So this is the final state. So it overlap. So that's it for this video. Thank you for watching. See you. Bye.